Along with our vacuum distillation, we're going to take the optical rotation of the sample that you distill. And so we're going to experimentally measure the chirality of the compound. Just to refresh your memory, enantiomers are non-superimposable mirror images, and they result from a chiral carbon. If an atom is chiral, it is tetrahedral and has 4 different groups on it. And you can have 2 non-superimposable structures for each chiral center, so you are aware of diastereomers. And so you look at the group and see if there's 4 different groups, and if so, then the atom is chiral. And in a structure, we'll also put a star next to an atom to indicate it's chiral. Chiral compounds physically rotate polarized light. So if you have the light is polarized, all of the waves are in the same plane. So they might be in different places in space, but they all are, let's say, perpendicular to the ground or parallel to the ground or at some angle in between. If you pass this light through a sample that has a chiral compound in it, the light will rotate one way or the other. And when I say it rotates the plane, so that if it was perpendicular to the ground, it's going to be off at some angle. When it does this, we call the compound optically active. So chiral and optically active are often used as synonyms. The direction of rotation cannot be determined from the structure of the compound. You can only get it from experimentally determining it. And we have 2 ways of indicating this. We can either use L for Lev rotary, and we put a minus in front. That means it rotates light in the negative direction, which would be counterclockwise. And we use D, and the symbol is plus because it rotates light in the positive direction, clockwise. And it's D stands for dextrorotary. So enantiomers, one is D and one is L, or you can say one is plus and the other one minus. The direction of rotation, as I said, can't be determined by the molecule, and you can't even look at the structure. You can't look at the structure and know how much it will rotate it. This is all experimentally determined. The R and S is just a designation that we give it so that we can talk to each other and know we're talking about the same structure when we're talking. Remember that enantiomers rotate light to the same degree, but in opposite directions. If you have 2 chiral centers, you have the opportunity for diastereomers or even mesocompounds, which would be a symmetrical compound with 2 chiral centers or more. Remember, if one carbon is a mirror and the other is not, they are not going to be enantiomers, they're going to be diastereomers. It's when both carbons are mirror images. So for instance, down here, this this compound, the enantiomer would be 2R, 3S, but its diastereomer has only 1 that is different. Enantiomers have the same chemical and physical characteristics except for the optical rotation. The only way you can have a different chemical reaction is if you're using a chiral substance. Diastereomers have different chemistry and different physical characteristics, so they're very easy to separate because of that. If you have a mixture, if it's 50-50, we call it a racemate. Anything other than 50-50 will have some rotation because one enantiomer will only cancel out an equal amount of the other, and then there's going to be something called the enantiomeric excess. Okay, we can, if it is a chiral, if a mixture of 2 enantiomers and one is in excess, we can actually measure the rotation. And if we know what the absolute rotation is, then we can say, well, this is optical purity. So you will often see that. Sometimes you will see EE after a number to indicate enantiomeric excess. Experimental rotation is done by shining plane polarized light through there and then measuring where it's coming through. And so we have an instrument called a polarimeter that will measure this, and we will do that. The variables that we use in optical rotation are going to be this. This is the specific rotation that would be the purity of the 100% pure compound under specific conditions. We just call it specific rotation, and that's what you find in documents. And then there's observed rotation, and observed rotation is dependent on how long the sample is, so how far the light is going through it, and then the concentration of the sample. I'll show you the formula in just a little bit. We usually use a D line from a sodium lamp. A polarimeter is kind of hard to use and it can be frustrating, but we'll get through it. You have to use an achiral solvent, so we usually use ethanol or dichloromethane. So what you're going to do is use a volumetric flask to precisely prepare a known concentration, and you pour it into the polarimetry tube. The tubes that we have a bubble catcher in there, so you can have bubbles in it. You then insert it into the polarimeter, and you start at 0 and you rotate in. You're going to see when you look through the eyepiece, you will see two halves of a circle split in half. And if it is a chiral compound, the two halves will be a different light intensity. So one might be dark and the other one light. What you have to do is rotate the polarimeter filter until you find the point at which you get the same intensity of light on either side, and you rotate back and forth and make sure. It's very hard to get a precise measurement there, but it just takes a little patience. Once if you do use a chiral solvent, you would have to it would mess things up completely. But even with an achiral solvent, what you do is you determine the rotation of that as a base, and you use it as a 0 in your machine. Here, if you don't have a digital machine, you would have to subtract it from your measurement. But we have a digital machine, and so it will actually, you can 0 it on your solvent and then take your measurement. So here it is. The sample goes through the light goes through the sample, and it comes out. The plane of light is rotated, and then the analyzer, you rotate it until the light goes through, and then you know how much it's been rotated. Okay, now this is the formula that we use for determining the specific rotation, or calculating what your observed rotation could be. For this formula, all you have to have is one unknown and 3 knowns, and the unknown then can be 3 knowns, and your unknown variable can be determined. This is the specific rotation, which is something for known compounds. It's documented in text, and it's supposed to be independent of concentration. And what we do is we take the specific rotation, that rotation that you have measured in the machine, and you divide it by the length of the tube, which is in decimeters, and by the concentration of the sample, which is in grams per milliliter. And once you take your measurement and you go and do the math here, you can find the specific rotation, and that can help you in identifying a compound. An optically pure compound is one that is only one enantiomer, and you can use that for identification. For instance, if you're doing a reaction and you don't know if it's SN1 or SN2 and you're using a chiral compound, you could test the product to see whether it's a D or L enantiomer and know the mechanism of the compound, the reaction. Okay, so now what we're going to do is look at mixtures. If you have a mixture of enantiomers, you can use the optical rotation to determine the concentration, because the amount that it rotates light is determined by the mole fraction in the compound. So if you have no rotation, it's got to be exactly 50-50, because then they cancel each other out perfectly. But if you have a mixture that has a little bit of one enantiomer but mostly another, you can figure out how much, by looking at the specific rotation, you can figure out how much you have of one, because the specific rotation is equal to the mole fraction times the specific rotation. So this would be for the mole fraction of the positive enantiomer, plus the mole fraction of the negative enantiomer times the specific rotation. Of course, this is in a negative direction and that's in a positive direction. Once you figure that out, what your specific rotation is, and let's say you measure 22.4, you can determine exactly how much you have by using a formula like this. So if the specific rotation is 53.9 and the sample of the mixture is negative 22.4, negative 22.4 is going to be the mole fraction of the positive enantiomer times the positive value, plus the mole fraction of the negative enantiomer, which is 1 minus the positive enantiomer, times the negative enantiomer's optical rotation. And then all you have to do, that's one equation in one unknown, and it's easy to solve using algebra. Remember, plus is the same as D and negative is the same as L, but they have no direct relationship with R or S. So R enantiomers can rotate at positive or negative. It can only be determined experimentally. You can find specific rotations in a lot of handbooks, including the CRC handbook and a lot of other reference books.